In this video, we're going to look at something called the Euler transformation of a series. But before we do that, we need to define something called the forward difference operator and then prove three supplementary results. So this forward difference operator is defined in the following way. So let's say we've got a sequence of real numbers, so I've indexed them by n. Then delta, so that's going to be our notation for this forward difference operator. So delta an is an minus an plus 1. And so there are other types of difference operators like this, like there's one where you have an plus 1 minus an, which I've used in some previous videos on discrete calculus, but this is the one that we're going to use right here. You can kind of think of this as some sort of derivative of a sequence. It's like a discrete derivative, because notice the closest the inputs of a sequence can get to each other are 1, and so we're subtracting two terms from the sequence that are as close together as they can be. Okay, so now the first thing that we want to prove is this thing which I have as my first bullet point. If I apply the forward difference operator n times to ak, I should get this object right here, which is the sum m equals 0 to n of minus 1 to the m, n choose m, a to the k plus m. So let's go ahead and see how that works. So this is the proof of my first bullet point, and we're going to do this by induction. So our induction hypothesis in this case will be the n equals 0 case, which is like applying the forward difference operator 0 times to ak, but applying it 0 times just gives us ak. But notice that's exactly equal to the sum m equals 0 to 0 of minus 1 to the m, and then here we have 0 choose m, and then a to the k plus m. So notice those two objects are the same, so that's exactly what we need. Okay, now let's make our induction hypothesis. Okay, so let's suppose this is true for n, and then we'll consider the n plus first case. So that means we're going to need n plus 1 times the forward difference operator evaluated at ak. But notice that's exactly equal to n times the forward difference operator evaluated at the forward difference operator of ak, or in other words, n applications of the forward difference operator to ak minus n forward difference operator n applications of the forward difference operator to ak plus 1. But now we can apply our induction hypothesis to get the following. So this term right here is going to be the sum m equals 0 to n of minus 1 to the m, n choose m, a to the k plus m. So that comes straight from the induction hypothesis. And this next term will also come straight from the induction hypothesis, just where we replace k with k plus 1. So that's going to give us the sum m equals 0 to n of minus 1 to the m, n choose m, a to the k plus 1 plus m. All right, great. Now we're going to go ahead and re-index this second sum. So notice that we can re-index this second sum. We'll take m and replace it with m minus 1. So notice that's going to give me the following. So my first sum is going to stay the same. I have m equals 0 to n minus 1 to the m, n choose m of a sub k plus m, minus the sum m equals 1 to n plus 1. So notice if I re-index m to m minus 1, that means I need to start at 1 instead of starting at 0. And now I'm going to have minus 1 to the m minus 1. But I'm going to go ahead and take this minus 1 here and use that to turn this into a plus. And now I'm going to have n choose m minus 1, and then a to the k plus m. Okay, like that. Now I can smush those two sums together, keeping in mind that I need to take out the first term and the last term, or I can also notice that if I can change the bounds here to n plus 1, because if m is equal to n plus 1, then this binomial coefficient is 0. And furthermore, I can change the bounds here to start at 0, because if m equals 0, then I can just assume that this is also like a 0 term as well. Okay, great. But now that's going to allow me to put these two sums together. So that's going to be the sum m equals 0 to n plus 1 of minus 1 to the n. And now I have the sum of two binomial coefficients, n choose m plus n choose m minus 1 of a sub k plus m. Okay, but now there's a very common binomial coefficient identity, the Pythagorean identity, that allows us to write this guy as n plus 1 choose m. Great, which is exactly what we want, and that actually finishes this proof because that puts this sum into the correct form. So we have established this equation, and now we're ready to prove this one. Okay, so let's prove this one. We can actually prove this directly by forming a telescoping series. So we have the sum L equals k to n of L choose k. Again, using my standard identity that defines binomial coefficients. So that's going to allow me to write this as the sum L equals k to n of L plus 1 choose k plus 1 minus L choose k plus 1. So you can think about this as really being a defining property of the binomial coefficients, and everything else follows from this. Okay, great. Now I'm going to split this up into two sums. So this is going to give me the sum L equals k to n of L plus 1 choose k plus 1 minus the sum L equals k to n of L choose k plus 1, like that. Now, the next thing that I want to do is re-index the first sum. So I will re-index the first sum by sending L to L minus 1. So here we'll take L is going to turn into L minus 1. And that's going to go ahead and change this to start at L equals k plus 1 and end at n plus 1. And now I'm going to have L choose k plus 1. Minus the sum L equals k to n of L choose k plus 1. All right. But now notice that these guys are exactly the same with one difference. This one ends at n plus 1 and this one starts at k. So everything else cancels except for the ending part of this sum and the starting part of this sum. So that means we can write this as n plus 1 choose k plus 1. That's the ending part of this sum minus the starting term from this sum, which is k choose k plus 1. But now k choose k plus 1 is 0 because the bottom of the binomial coefficient is larger than the top of the binomial coefficient. So we end up with n plus 1 choose k plus 1, which is exactly what we wanted to. Okay, so now we're done with this equation. We'll move on to this one. Okay, so now let's move on to this third one. We're going to prove this by induction. And so our base case will be the case when m equals 0. So let's see what happens when m equals 0. So that's going to give us the sum n equals 0 to infinity of n choose 0 x to the n. So that's what's happening on the left-hand side of this. But that's exactly equal to the sum n equals 0 to infinity of x to the n, because n choose 0 is 1. But notice that that is a geometric series. We get 1 over 1 minus x, which is x to the 0 over 1 minus x to the 0 plus 1. So the induction hypothesis is satisfied. So we've established the base case. Now we're going to move on to the induction step, but I'm going to erase the board for that because we're going to need all of this in order to prove that. Okay, so now let's make our induction hypothesis. So let's suppose for m equals k, we know that this statement is true. So in other words, we know that the sum from n equals k to infinity of n choose k, x to the n, is the same thing as x to the k over 1 minus x to the k plus 1. And now what we're going to do is we're going to change the right-hand side to make it look like the k plus first case, and then we're going to do the same thing to the left-hand side. So that means we're going to multiply by, so to turn the right-hand side into the right thing, it will be x over 1 minus x. But notice x times 1... x over 1 minus x is the same thing as x times 1 over 1 minus x, but then again that's a geometric series, so that's going to be the same thing as x times the sum n equals 0 to infinity of x to the n. So now we're going to take this version and multiply it to the right hand side of this equation, and we're going to take this version and we're going to multiply it to the left hand side of this equation. Okay, so let's see what that gives us. So if I take this guy and multiply it to the right-hand side of the equation, that's going to give me x to the k plus 1 over 1 minus x to the k plus 2. Okay, but that's the same thing as x over 1 minus x times this guy. So the sum n equals k to infinity of n choose k, x to the n. But rewriting this guy as a series, that's the same thing as x times this sum n equals 0 to infinity of x to the n times this sum n equals k to infinity of n choose k, x to the n. So we've got a product of two infinite series. So now I'm going to gloss over a little bit of the details, but if you go ahead and look up the formula for the Cauchy product of series, that'll give you an idea how to take the product of these two infinite series. And what you'll end up with in the end is that this is equal to x times the sum k to infinity of the sum L equals k to n of L choose k times x to the n. Okay, so that's what you get when you take this this product of infinite series. So notice we get an infinite series on the outside and then a finite series on the inside. Okay, but now we can apply this formula, which we just got done proving, and this is going to be equal to x, and then the sum n equals k to infinity of n plus 1 choose k plus 1 x to the n. Okay, great. But the next thing that I can do is I can multiply this x in, and that's going to give me x to the n plus 1. And then finally, I can re-index. So I'll re-index by sending n to n minus 1, and that's going to turn this into the sum n equals k plus 1 to infinity of n choose k plus 1 x to the n. So now let's go ahead and look at the extreme right and left hand side of the equation, and notice that that is exactly this, where k has been replaced with k plus 1, which is exactly what we need to do to finish this induction proof. Okay, so now we're done with this and we're ready to get on proving the main theorem. Okay, so we've done our preparatory results. Now we're ready for our main theorem. So we'll go ahead and just start at the right-hand side of this. So let's say we have the sum n equals 0 to infinity of the forward difference operator applied n times to a0 over 2 to the n plus 1. Okay? But notice that's going to be equal to the sum n equals 0 to infinity of 1 over 2 to the n plus 1. And now we have this formula for the forward difference operator having been applied n times. So that's going to give me the sum m equals 0 to n of minus 1 to the m, and then n choose m, a to the a sub 0 plus m, so in other words, a sub m. Okay, good. But now I'm going to turn this into a double sum instead of like this iterated sum. So I've got this sum n equals 0 to infinity, and then this sum m equals 0 to n of minus 1 to the m over 2 to the n plus 1. Then I have n choose m, a sub m. Now the next thing that I'm going to do is change the order of my summation. So notice right now I have this happening. I have 0 is less than or equal to m, which is less than or equal to n. So if I change my order of summation, that means n has to start at m. So that's going to give me this. This will be the sum m equals 0 to infinity. The sum n equals m to infinity. And now I have minus 1 to the m over 2 to the n plus 1. And then n choose m, a sub m. Now what I want to do is take all the parts of this sum that have to do with m and bring them out. And that's going to give me this. So I'll have the sum m equals 0 to infinity of minus 1 to the m, a sub m. And I'm actually going to go ahead and bring a half out as well. So I'll bring a half out and I'll write this as 1 over 2. And that's going to leave me with the sum n equals m to infinity of n choose m times 1/2 to the n. Okay, great. But notice that this guy over here is exactly this thing where I've set x equal to 1/2. So that means I can replace this sum where x is equal to 1/2 with this closed formula with x equals 1/2. So let's see what that's going to give us. So now we have the sum m equals 0 to infinity of minus 1 to the m, a sub m over 2. And now I'm going to have 1/2 to the m power over 1 minus 1/2. Well, that's obviously another half to the m plus 1 power. Okay? But notice that that's going to cancel down to just a 1/2 in the denominator, which is going to cancel this 2 in the denominator. So all of this cancels, leaving me with the sum m equals 0 to infinity of minus 1 to the m, a sub m, which finishes the proof of this transformation. Okay, great. So I'm going to clean up the board and then we're going to look at an application of this. Okay, so for our application, we're going to look at this sum. So it's the alternating harmonic series. So the sum n equals 0 to infinity of minus 1 to the n over n plus 1. Okay, so this is like obviously 1 minus half plus third minus quarter plus fifth minus sixth plus seventh and so on and so forth. And we'll actually get the formula for this, but we'll see that this allows us to write this sum as another sum via the Euler transformation, which is like super nice. Okay, so the first thing that we want to notice is that here we have a sub n is 1 over n plus 1. And then we want to make the following claim. Actually, I'm going to go ahead and write this as a sub k equals k plus 1. And now I want to make the following claim. And that is if I apply the forward difference operator n times to a sub k, I should get n factorial over k plus 1 times all the way up to k plus 1 plus n. So I've got that rising product in the denominator. So I'm going to go ahead and prove this by induction on n. And this is more of a sketch. There might be some details that you want to work into this if you want to. But notice if we do induction on n, our base case will be n equals 0, which again will be 0 times the forward difference operator applied to ak, which is going to be 0 factorial over k plus 1, which is exactly 1 over k plus 1, which is what we need it to be. Now the next thing that we want to do is suppose that it's true for n and prove that it's true for n plus 1. So let's take the forward difference operator n plus 1 times applied to a sub k. But notice that's going to give us the forward difference operator n times applied to the forward difference operator applied to a sub k. But that's going to give us n times the forward difference operator a sub k minus a sub k plus 1. But by our induction hypothesis, we know how n times the forward difference operator acts on each of these. So that's going to go ahead and give us n factorial over k plus 1 all the way up to k plus 1 plus n minus n factorial and then k plus 2 all the way up to k plus 2 plus n. Okay, good. And then if you do this difference of these two fractions, it's easy to check that this is indeed n plus 1 factorial over k plus 1 all the way up to k plus 2 plus n, which is exactly what we need it to be. So we have proven this claim, and the next thing that we want to do is apply this to k equals 0. So notice that means that the forward difference operator to a sub 0 is going to be equal to n factorial over 0 plus 1, 0 plus 2, all the way up to 0 plus 1 plus n. In other words, n plus 1 factorial, which is equal to 1 over n plus 1. Okay, good. So now that we have that out of the way, we can apply this Euler transformation. And so that's going to give us the sum n equals 0 to infinity of minus 1 to the n over n plus 1. So that's our original sum, is going to be equal to the sum n equals 0 to infinity of the forward difference operator applied n times to a0, but we showed that that was 1 over n plus 1, and then all of that's over 2 to the n plus 1. So this is 1 over 2 to the n plus 1 times n plus 1. Okay, great. So now we've proven the equality of each of those series. And sometimes this series is a little bit trickier to get the sum of than this series. So it's really nice that we have the equality of these two series. Okay, I'm going to clean up the board and then we will finish this off by finding this value. Okay, so on the last board we used the Euler transformation of a series to show that these two series had equal sums. And so now I'm going to go ahead and use like fairly elementary methods to find the sum of this second version. There are some other videos, including some that I've done, where I find the sum of this first series. So obviously these are the same, but I think this is maybe a new approach. Not to the world, but to YouTube videos. Okay, great. So let's notice that this is the same thing as the sum n equals 0 to infinity of minus 1 to the n over n plus 1, and then x to the n plus 1, where we have evaluated that from 1 to 0, or from 0 to 1. But we can see that that is the same thing as the sum n equals 0 to infinity of minus 1 to the n times the antiderivative from 0 to 1, the integral from 0 to 1 of x to the n dx. Okay? But the next thing that we can do is bring the sum inside the integral, because between 0 and 1 this is absolutely convergent. So this is going to give us the sum n equals So this is going to give us the integral from 0 to 1 of the sum n equals 0 to infinity of, and I'm going to write this as minus x to the n dx. But again, that's a geometric series, so that's the integral from 0 to 1 of 1 over 1 plus x dx, which is going to give us the natural log of 1 plus x evaluated from 0 to 1, which gives us the natural log of 2. Okay, so now let's look at the extreme left-hand side and the extreme right-hand side, and we've proven that the sum of this series is equal to the natural log of 2. All right, this is a good place to stop.